The Medina-Julian oscillation is the largest element of the intraseasonal variability in the tropical atmosphere. It was discovered in 1971 by Roland, Madden and Julian of the American National Center for Atmospheric Research. It is a large-scale coupling between atmospheric circulation and tropical deep convection. Unlike a standing pattern like the LNIA ±O Southern Oscillation, the Medina-Julian oscillation is a traveling pattern that propagates eastward at approximately 4 to 8 m per second through the atmosphere above the warm parts of the Indian and Pacific Oceans. This overall circulation pattern manifests itself most clearly as anomalous rainfall. The Medina-Julian oscillation is characterized by an eastward progression of large regions of both enhanced and suppressed tropical rainfall, observed mainly over the Indian and Pacific Ocean. The anomalous rainfall is usually first evident over the western Indian Ocean, and remains evident as it propagates over the very warm ocean waters of the western and central tropical Pacific. This pattern of tropical rainfall then generally becomes nondescript as it moves over the cooler ocean waters of the eastern Pacific, but occasionally reappears at low amplitude over the tropical Atlantic, and higher amplitude over the Indian Ocean. The wet phase of enhanced convection and precipitation is followed by a dry phase, where thunderstorm activity is suppressed. Each cycle lasts approximately 30 circumflex 60 days. Because of this pattern, the Medina-Julian oscillation is also known as the 30 circumflex 60-day oscillation, 30 circumflex 60-day wave, or intraseasonal oscillation. Distinct patterns of low-level and upper-level atmospheric circulation anomalies accompany the MJO-related pattern of enhanced or decreased tropical rainfall across the tropics. These circulation features extend around the globe and are not confined to only the eastern hemisphere. The Medina-Julian oscillation moves eastward at between 4 m per second and 8 m per second across the tropics, crossing the Earth's tropics in 30 to 60 days, with the active phase of the MJO tracked by the degree of outgoing long-wave radiation, which is measured by infrared sensing geostationary weather satellites. The lower the amount of outgoing long-wave radiation, the stronger the thunderstorm complexes, or convection, is within that region. Enhanced surface westerly winds occur near the west side of the active convection. Ocean currents, up to 100 meters in depth from the ocean surface, follow in phase with the east wind component of the surface winds. In advance, or to the east, of the MJO enhanced activity, winds aloft are westerly. In its wake, or to the west of the enhanced rainfall area, winds aloft are easterly. These wind changes aloft are due to the divergence present over the active thunderstorms during the enhanced phase. Its direct influence can be tracked poleward as far as 30 degrees latitude from the equator in both northern and southern hemispheres, propagating outward from its origin near the equator at around 1 degree latitude, or 111 kilometers, per day. During the northern hemisphere's summer season, the MJO-related effects on the Indian and West African summer monsoon are well documented. MJO-related effects on the North American summer monsoon also occur, though they are relatively weaker. MJO-related impacts on the North American summer precipitation patterns are strongly linked to meridional adjustments of the precipitation pattern in the eastern tropical Pacific. A strong relationship between the leading mode of intraseasonal variability of the North American monsoon system, the MJO, and the points of origin of tropical cyclones is also present. A period of warming sea surface temperatures are found 5 to 10 days prior to a strengthening of MJO-related precipitation across southern Asia. A break in the Asian monsoon, normally during the month of July, has been attributed to the Medina-Julian oscillation, after its enhanced phase moves off to the east of the region into the open tropical Pacific Ocean.